Hello everyone, welcome back to this class. Okay, so today we will continue our discussions on reaction diffusion equations. And this is a really great tool to model, spatial dynamics in ecological systems and more broadly biological systems. So we have specifically looked at this model, right? Logistic model in the reaction term. And then we have a diffusion term. So for the large part that we're, I'm doing analytical like calculations and where I'm writing equations, I will restrict myself to one dimensions. But simulations we will be sort of, doing in two dimensions. Okay. So here I want to emphasize that there are indeed fundamental differences between 1 and 2 dimensions for certain cases. Okay. So when that is indeed the case, I will of course tell you. But for a large part, whatever we do in the 1D can also be easily sort of applied to 2D as well. Okay. So with that caveat about dimensionality, so I have written down the Fisher-Kolmogorov equation, which is the reaction diffusion equation, where the reaction term is a logistic model. Can we discuss the idea of homogeneous equilibrium? Which are basically mean field equilibrium set across the entire space. So for all values of x, we set 0 or k, depending on whichever, this would be the homogeneous extinction equilibrium. And if we choose this would be homogeneous carrying capacity equilibrium. I have told you okay, and then we did two things last time. One is that we made an attempt at linear stability analysis. Right? And what did we find? In fact, if I were to replace this by a more general function f of n, where n does depend on space and time. Okay, and then if I look at a perturbation n, n star any of the mean field equilibrium plus a spatially dependent. I don't mean to write eta. I mean to write n. Okay, a spatially dependent perturbation, a small perturbation. What we found was that the following equation, where eta is small, and not eta, sorry, n of x is small everywhere in space, we were able to write down this partial differential equation now. The rate of change of the perturbation at each location is given by alpha times f prime at n, alpha times n of x comma t plus the diffusion of the perturbation. So we derived this on Saturday's class. This is an approximate equation because it's a linear approximation. we are assuming that n is sufficiently small that I can ignore the higher order terms. This is what we found. And then I asked you to sort of, we again discussed what if the perturbation itself was homogeneous, but we trivially found that in that case, the diffusion makes no difference. So therefore, for homogeneous perturbations, the stability of the original mean field model does not change. For homogeneous perturbations. The stability of mean field equilibrium continues to hold true. Right? So that was a nice result, although fairly trivial. Now let us see, and then we also wondered what happens if this NXT is not a homogeneous equilibrium anymore. I showed you examples with simulations. From the simulations, what was our conclusions? Non-homogeneous perturbations. So what was our conclusion from simulations? We, I think the way, at least in the logistic model, right? Logistic model in space, what we found that n star is equal to 0 continues to be unstable, at least for the similar, for few examples we tried. On the other hand, n star is equal to k continues to be stable. So at least from the simulations, it appeared like even when we have non-homogeneous perturbations, our results do not change. Okay, and then I asked you more difficult question. This is for the simulations of Fisher-Kolmogorov equation, right? And then in the lab work, I asked you what happens for harvesting model in the bistable region, right? I hope you have found some answers. Model with space in the bistable region. Okay. So we will discuss this again later because I have given the deadline of tomorrow for people to complete this. We will discuss this later. Let us now try to understand the same question a bit more mathematically. Okay. So I had requested you all to read up on Fourier series. I think it's called Fourier series in the right French pronunciation, but but I'll probably get this wrong. So I'm going to say Fourier, like most of us do. Okay, so to really understand that, we need to learn an entirely new technique now. If you haven't learned, if you haven't revised, I'll give you a quick overview of what are Fourier series. And this is an extremely fascinating mathematical idea. The idea is fairly simple. So start with the fact that we all know what is a sine and a cosine functions. So cosine function is a periodic function that looks like this, and so on. This is 0. This is pi by 2. This is pi. This is minus pi by 2, and so on. Okay. So cosine function is a periodic function with a period 2 pi, and so it's a sine function. Okay, sine and cosine functions are, for all practical purposes, same functions, except that they are phase shifted. So if I take the sine function and sort of, pull it towards left here, I get a by 90 degrees or pi by 2 radians, I will have cosine function. So in that sense, they are basically sort of, have all the same properties. Okay, in terms of the function, of course, they are shifted by pi by 2. Okay, so now here is the very interesting sort of, theorem that Fourier came up with. He basically said that you take any periodic function, f of, let's use g, okay, g of x. He said that, let's say the period BL, or period I think is 2L, sorry. Okay, period is up to L minus L to L. Okay, after that it repeats. Just like cosine and sine are period to minus pi to pi, you can think of exactly the same way. We can modify this from 0 to L and so on and so forth without really any problem. So it has to be just of period 2L. Now with that, so he said something really remarkable, which is that this function can be written in this form. It can always be written as a superposition of various sine and cosine functions. Okay. So I'm using the same notation from the video I had sent you, just so that I don't keep changing. So basically the first term in the Fourier series is that any given function has some constant value a0. It is just to take things up and down. As you know, sine and cosine have, vary from -1 to 1 in the y-axis, right? Okay, so this helps you add some constant value. Of course, you also have the amplitude here. So you can take a bunch of cosine curves, okay, with various periods, okay, and then if you add them up with various coefficients, you will, and then likewise, if we have a various bunch of sines, and then again you do the same thing, you basically can construct any mathematical periodic function. It is really remarkable in many, many ways. And I hope that you also saw the example of the square wave that was described by him. Okay, so I will not go into details of why this is true and why this is not true and how this actually comes to be true. But the broad idea is that, if you think in terms of broadly in terms of functions, there are, let me give you an example. Maybe an example might help you. Let's say if I have a coordinate, right, x comma y. Okay, to define this coordinate x comma y, I need an x-axis and a y-axis, right? So if I have an x-axis and if I have a y-axis, I can construct any point in a two-dimensional world. Now, if I had, if I had the three-dimensional world, the coordinates will then become x, y, and z, right? So with the help of three axes, x, y, and z, I can construct any point in the three-dimensional space. Now, instead of points, think of now functions. Okay. Okay, just like there are three independent axes, three independent directions from which you can construct any coordinate in a three-dimensional world. If you think of function space, any function can be constructed from a combination of various sines and cosines, except that unlike we needed only three finite number of axes, right? Here, what you need are actually infinitely large number of sines and cosines. Okay, so they form the basis function, just like these are called the basis coordinates. Sines and cosine form basis of function space, and using them, we can actually construct any mathematical periodic function. And in fact, Fourier side, I can also be generalized for non-periodic functions. They're called Fourier transforms. Okay, that's the basic idea. So, and then how do, can I ask, okay, fine, there's this theorem, how do I really know these values? A, N, B, N, and so on. It turns out that it is indeed possible. Again, that video gives you all the, formulas. So I'll just write that down for the sake of completeness. So this integration will give you what is A0. And in general, for all other ANs, you can use this integration.
Sir, I think for A0, it's 1 by 2L.
There is 2, is it? Okay, sorry, thank you very much. Okay, so again, you do the same integration over the entire period. So to know AN, you need to multiply with the corresponding cosine basis function. Okay. And this is actually very easy to prove, by the way, this formula, if you know the properties of sines and cosines. So one interesting property of sines and cosines is if you multiply two sine functions with different periods, and if you integrate them over its period, we'll always get 0. Okay. Or let's take the simple example of sine and cosine themselves. If you multiply sine and cosine, sine x times cosine x, now integrate this function between its period 0 to pi or minus pi to pi, whatever the period you choose, the product will always be 0. Okay, and that you can probably see just by looking at them. Okay, and this idea is true for any two sine functions you take, as long as their periods are different. Okay, so and that will give you these very simple results. Okay, so this is to sort of just to revive. There is a basic idea that any function can be written as a summation of sines and cosines, and there are no cross terms. There is nothing like a sine and cosine term. There are no interaction terms. Okay. So what do we do with this? Let me just tell you one more thing that might be useful and I might use. I'm not entirely sure. So you may also know the following. Okay. Another very interesting mathematical tool. E power ikx. Something you may have learned in your high school 12th, if we had mathematics in 12th. Okay. This is a really beautiful equation, and using this, what you can do is you can write cosine and sine in terms of exponentials. Okay, for example, cosine of kx turns out to be e power ikx plus e power minus ikx divided by 2. Whereas, so this is not essential if you have never come across this. Okay, but if you have come across, it's useful to revise this. Divided by 2i. Now, if you go back to the Fourier series and replace cosine of this by this formula in terms of e's, exponentials, and likewise sine, what you can show is that g of x can be written as, again, a constant, plus k is equal to minus infinity to plus infinity, ck e power minus plus. So it can be written in this form. Okay, I'm sorry. This should have, what is that? K pi x pi l. I have just changed the indices from n to k. Please bear with me on that. Okay. So you can write, in a compact form. This notation this is also Fourier series, exactly same as the one I wrote previously, except this helps me write this in a more compact form. Okay. And ck also has an interesting property that c of minus k is basically conjugate of c. Okay. And in fact, this is equal to c of k, in fact, is equal to ak plus ibk. Okay, please verify this. I'll use it as a small exercise for those for those who are interested, if you haven't come across this. Optional. So for today, I hope not to use this at all. Okay. But this is very useful to know in general when we are using Fourier series. Okay. So any questions on Fourier series? Broad questions. You don't have to worry about the mathematical details. Any broad questions of the concept of Fourier series? Okay, if there are no questions, I will go forward and show you a visual demonstration of how Fourier series works. Okay, so what do I mean by that? Let me continue a demonstration. Okay, so what does this really mean? You might still be wondering. Let's please make it more concrete, right? Why on earth would I want to even do something like this? So here is the basic idea. Okay, let's take an example. Okay, so let's say I have this function sine 2x. Okay, so all of you know how this would look like. Like I just plot this sine 2x. Let me not write it this way. Let me write this in a more formal way: 2 pi x omega. I'm going to do it a slightly different way. Okay, omega 1. Okay, now what does this mean? This means that this is basically a sine wave, okay, which has a frequency of omega 1. Okay, this means that this is a sine wave of frequency omega 1. Okay, y1 of x. Oh, since we're talking about okay, maybe let's just do time, because the thing is, I also have an R code that I want to show. I just made that in the form of time, so I'm going to stick to this. Think of it as time. Okay. Okay. So, but you can just replace time by space here. It makes no difference whatsoever. Okay. So think of there is some wave, which is following a sine wave with a frequency omega 1. Okay. So way to think about frequency is that it's completes cycle. Sine is a periodic cycle, right? So it completes one cycle in 1 time unit. That's what this means. Again, omega 1 time units. That's what this means. Am I right about that interpretation, by the way? I hope I haven't messed up my words.
Sir, I suppose omega should be replaced by f.
Frequency, no? Yeah, you're right. Omega is usually in the denominator, right? Okay, it's a very good point. Sorry. Thank you very much. Okay. Omega is, okay, is this fine now? So omega would be 2 pi f1 would have been omega, right? Is that what you meant?
Yes, sir.
Okay, thank you very much. Yeah. The frequency omega 1. Okay, so what this basically means is that sine would complete one cycle in f1 time, f1 no in 1 time unit there will be f1 cycles. Okay, is that clear to everyone? F1 cycles of sine. So in the simplest case, f1 is equal to 1. In one time unit there will be one complete period of sine. If f1 was 2, there would be 2 cycles of sine wave in 1 time unit, and so on. If f1 was 100, there would be 100 cycles of sine in 1 time unit. Okay. Now let's consider another wave. Again, sine, to make life easy, I could have chosen cosine entirely. f2. This is with f2. There are 2 waves, f1 and f2. Now what I will do is I will just superpose them. So how this looks like, this will complete one f1 cycles in 1 time. This will complete f2 cycles in 1 time. So what you have done is you have superpose them. And sometimes this thing can have very awkward shapes. For example, you know how a typical sine looks like this, right? Nice. But when you superpose them, you know, the two of different frequencies can actually have shapes like this. Depending on how many you superpose, how many sort of, how many frequencies you add and what are the amplitudes of those frequencies. It can actually look pretty random, although there was nothing random in the equation I wrote. Okay. So this is possible. Now imagine that I was given only this combined wave. I don't know what are the individual waves that somebody generated. Imagine that I just chose some value of f1, some value of f2, a1, a2. There are basically 4 values I'm choosing, right? a1, a2, f1, f2, 4 parameters in this very simple superposition of 2 waves. Imagine I gave you just that. I gave you value of t and corresponding values of y. Okay, so I will have, imagine I gave you a vector like this, t and y, lots of time values corresponding y values that corresponds to this. This is t, this is y1, for example. What I have now is y, and this is t. Okay, so can you tell me from this, can we know a1, f1? What was the frequency? What was the amplitude? What was the second frequency? What was the third amplitude? And in fact, there are many, infinitely large. How do we know this? So the basic idea is now goes back to Fourier. He says that you can compute all those from these formulas. Okay, so you can, even though the person who made the superposition did not tell you, if the person gave you the data, you must be able to decompose and find out what were the values of every one of those A's, B's. Okay. And let me just demonstrate. Is the idea of Fourier transform clear now? I will now just demonstrate this using a simple OR code. Okay.
So just a quick question. How do we find
Sure.
the values of f from this? So all these 3 equations that Fourier gave is for a0, an, and bn. But how do we find f? Won't we have a Fourier transform for that?
That's a hold on first. I'll just share the. Yeah, that's a good question. But let's go back to the formula that Fourier gave you. Okay, imagine that this equation will in these equations, n's can go from really 1 to infinitely large, right? Imagine that there are some n's I have not used when I was creating the wave. Okay, what will the corresponding an's be? Okay, let's stick to entirely sine only. Okay, for the make our discussion easy. Imagine that I used n is equal to 1, 3, and 5. Okay, but not 2, 4, and 6. What will be b1 and b3 and b5? If I have not used when I was constructing it,
They'll be 0.
They will be 0, right? So basically, whenever I any frequency that I did not use will give you an amplitude 0, right?
Right, that works. Yeah.
That basically they go together, right? Because they're coupled. Huh? So any frequency I did not use, their values will be 0. That's the basic idea. So let me just demonstrate that with very, very simple code. Are you able to see this now? Are you able to see this in our studio? Hello?
Yes.
Yeah, thank you very much. Yeah. So sticking with the same notation, I will just change omega to f. Okay. Okay. So let's just go this one by one. So I have created a time array from 0 to 1 time units at a fairly large frequency. Okay. So basically, between 0 and 1, I have 1,000 values. Okay. And then the length of the length of the t will be actually 1,001 because it includes 0 and 1 as well. Okay. So I have created a time array and the length of the time array is capital T. And what I am also doing is I am generating a bunch of random numbers, normal distribution random numbers. T of them, which is the length of the time I have chosen, which means 0, second argument here, and a standard deviation of 0.1. Okay. And then so I'm going to now generate two waves. I have chosen arbitrarily two frequencies. F1 is 50 and F2 is 200. Okay. Meaning in one time unit, there will be 50 cycles of the first one and 200 of the second. Okay. And note that I'm just going from 0 to 1 time unit. Okay. So I will have so many cycles of both of them. And what I have now done is I have superposed these two waves. Y is equal to, but with a different amplitude. For the first wave, sine 2 pi f1t, I have an amplitude, a fairly small amplitude of 0.1. For the second wave with frequency 200, I have amplitude of 0.5. And what I have also done is I have just added some random numbers to make things even messier. And then I'm going to plot them. Okay. So this entire thing I'm now going to first execute. Okay. So this is how a superposition of two waves that I created looks like. Okay. Because it is only a superposition of two waves, it does look periodic. But what you can clearly see is that there is some amount of distortions to it in many ways. One way being that there are the spikes kind of things. The second way being that the amplitude is going up and down, right? Okay, in somewhat not very regular fashion, because this has slightly longer trough here compared to here. It has only a different length. This has even different length, right? Only one, different widths of these troughs. Okay, so clearly it's not a straightforward periodic wave anymore. Okay, now this is what we have plotted. This now somebody has just, let us say, given you t and y, nothing else. Okay, so what do you do? So what I have done here is, R has a function called FFT. If you give any signal or a wave, it computes the Fourier transform. But here is the thing: Fourier transform in general. So I showed you this, the complex version of the Fourier transform, right? So the Fourier coefficients in that form will actually have complex numbers as well. So the FFTY in this case could be complex. Okay. So what I have done next is, after calculating, I've stored the Fourier transform of the Y in a variable called FFTY. And then what I do is I'm only computing the absolute values of the FFTY. And that is stored in a variable called spec Y. So there is a reason why I call this spec Y. If you take the Fourier transform and if you take the absolute value, I should also square, I think. Is that right? Does somebody remember spectral function? I think the square of the Fourier transform, the absolute square of the Fourier transform is called spectral function, right? So I think we take a square. Okay, and then you plot that, plot that. So what is this plot? So this spec Y will have a length is equal to length of your initial time values. Okay, and it has another feature that it actually is a mirror image between 0 to 2 by 2, t by 2, and t by 2 to t. Okay, it will look exactly same on the other half side. So therefore, a mirror image of what you find here. Therefore, I'm plotting only from 0 to t by 2, and then let's see if it picks up the right frequencies. Let's execute the Fourier transform part of the code. Look at this. What did you find? You find that there are two spikes, one at roughly 100 by 2, right? Another one at 200. Exactly the two inputs we have chosen. Okay, so if I am right to get the exact, with this simple thing, you will get the relative strengths of the two waves correctly, but you will not get the absolute values correctly. If I am right, if you divide it by t, I think you will get the correct values. I will check that, and when I upload the code, I will make sure I will also get that right. Okay. So as you can see clearly, there are two peaks this is showing. So x-axis is, think of x-axis as n, basically index n. Okay, index n, and then it is showing exactly at the two, or the index frequency f that I mentioned, right? All possible frequency f's, of which only 50 and 200 have a finite amplitude. Everybody else is 0. Is that clear to everyone? We can also change, how well does it work? Let's see, 100 and 200, does it work? See, 100 and 200 works. Let's change the amplitude. Let's make them equal. Does it work? See, there is of course small difference because of stochasticity. So because of the stochasticity that I add, you will find a small difference. See, every time you run, there will be some differences in the computation. Except I don't know why this is always higher than this. I don't know, that shouldn't usually happen. Okay, so every time I'm running, it's and qualitatively it's roughly it's picking up the right stuff. And you can also try different, 400, 100, does it work well? Yes. Okay, so basically this is the idea. It picks the not only the frequencies but also the amplitudes fairly well. I don't know why the amplitude is slightly messed up. So if I remove the square, you will see some patterns more clearly. We'll see that there is a lot of noise here. Why do you think we are finding this noise here?
That's because of the R number.
Yeah, that's because of the random numbers that I have added in, right? Okay, exactly. So if I did not add this, you will find them to be 0. Okay. But any real data will always have some randomness. Okay. So this picks up. So this is just to, if you have never come across Fourier series and if you had never played around with it, I thought this would be useful to demonstrate. Any questions? I actually still don't know why the amplitudes are not coming out to be sort of same. There is a difference, no? It's like, 5:4 ratio. That shouldn't have happened. Maybe there is some mistake in the code. I will see and get back to you. If anybody knows, let me know if I have made any mistake. There's consistently a difference, right? So the ratio must have been now 2, but it's not really not 2, 125 and 175. Okay, I will also try maybe in MATLAB also and see if I find similar issue. What happens if I remove the random numbers? Even then there's a problem. So anyway, I don't know if any of you know, please let me know. I don't know why this is happening. Okay, this is how this is the demonstration of Fourier series. Okay. Okay, now let me go back. So how many of you have done Fourier series sometime? Fourier series, Fourier transforms before? If you can raise your hands, I will know. No one? Oh, some of you. Okay, Dharanish. Okay, fairly half of the class, right? Okay, great. Okay. This must be, is this basically in your undergrad sort of math course in the beginning, or is it in a more specialized course?
I think this came in a lot of physics courses.
Okay. And how about others who are not physics majors?
It was a signal processing course for me.
Okay. I mean, then you know everything about Fourier transforms, much, 100 times more than what I know. Okay. Okay. So anyway, for those who have never done before, which is half the class, I hope this small tutorial was helpful. Okay. So let's now, why am I doing all of this, right? Suddenly, let's go back and recall where we were. So remember, we were somewhere here, right? So we had this equation. We want to move forward now, right? So I think there is a hint that I may have given you by now. Any function can be right? Any function can be. So let's just write down the linearized. So linearized PDE we have for the perturbation is this. This is what we have. We only knew how to deal with homogeneous perturbations. So we now want to deal with, homogeneous perturbation. You remember that we also, when we were simulating, we also used periodic boundaries, right? So that justifies us. So that, if somebody were to make now an arbitrary perturbation nx, we can, I hope all of you will agree that, at time t is equal to 0, somebody has made a perturbation, and that perturbation basically has summation of sine and cosines. Okay, that's the basic idea. So we can write this in the following form. Okay, the second e power I pi kx by L, right? The summation. Is everyone fine with this? Therefore, we can write any perturbation in this form. Okay. So let's do something simple right now. Let's consider a very specific perturbation. Okay, consider a very specific sinusoidal perturbation. So I will still, I have decided not to use this for the time being. Again, just to keep the overall math slightly more intuitive. So let's say that n of x is an times sine k. Oh, I'm going to use k. Okay, k by x by L. Is that fine? So I'm going to use this very specific perturbation, and let us see what happens if I did, instead of a homogeneous perturbation, let us say we have a periodic perturbation, and let us see what happens to the perturbation. Does this perturbation decay, or does it, die off? Okay, so let's compute the left hand side first. Okay, what is dou n by dt? If I do this, so time derivative of this. What is the time derivative of this? It's 0. So there must have been a coefficient ck here. So clearly this step doesn't depend on time. What about AK? So again, think of the space. We have the space, right? Okay. So this is the homogeneous equilibrium. Okay, let's say this is x-axis, this is y-axis. So the z-axis is the state variable n. Okay. Let's say we are at 0 right now. So what we have, pardon my writing skills, think of a perturbation that is like this now. This is n perturbation, right? At time t is equal to 0. Okay. So the only way this will change over time is if the amplitude AK changes over time, right? Okay. So this dn by dt basically becomes k by x by L dak by dt. Is that fine? That means AK should be thought of as depending on time. So time t is equal to 0. This was the perturbation. It doesn't mean that this remains same every time. No. So AK will change over time. Therefore, the time derivative goes like this. Now, what about the first term? alpha times n, that doesn't really change much. Alpha times n is nothing but alpha times ak sine k pi x by L. That's fine. Now we have the diffusion term. So this is a spatial derivative. If I apply the spatial derivative to the perturbation, what do I get? Does ak depend on x? No, x dependence comes entirely from sine. Therefore, ak remains exactly the way it is. And what happens if you take the sine and take the derivative 2 times? You actually get the sine back, but with a minus sign and with a coefficient which is the square of the terms in sine. Okay, let us simplify this. This basically becomes minus ak k square pi square divided by L square sine of k pi x by L. Is everyone fine? So basically, for those of you who have recall that d square by dx square of sine omega x is equal to minus omega square sine omega x. I've just used that here. Okay. So we have basically now all the 3 terms, right? Left hand side. This is the right hand side first term, right hand second term. Just put them all together. So you have d ak by dt on the left hand side times sine k pi x by L is equal to, first term is alpha times ak times sine k pi x by L minus ak k square pi square L square. So if I'm making any algebraic mistakes, please do let me know. I wish I wrote all this in the same order every time. Okay, fine. So what I'm going to do now is the obvious thing, which is I see that there is a sign everywhere. So I'm going to take this off. Okay. So if I do this, what am I left with now? dak by dt. This tells me the rate of change of the amplitude of the sign perturbation I have made. That is given by alpha times ak, just the regular exponential term with alpha, which is same as what we had for the mean field model, minus some additional terms though, minus k square pi square by L square times ak. So this is equal to alpha minus k square pi square by L square times ak. Is this clear to everyone? Any questions? So just see what we have done. I think what we have done is really amazing. Okay. Rather, what Fourier helped us do was something really amazing, right? We started off with a partial differential equation, which is always very messy. Okay. And what we have ended up with is an ordinary differential equation. By considering a single spatial wave, a single sine wave as a perturbation. Is that clear to everyone what we have done? Okay, this is a really amazing use of Fourier transforms. Okay, and what this tells is that the amplitude, the rate of decay or the rate of growth of this amplitude of the kth wave is a simple exponential, simple exponential form for a simple exponential growth or decay. When does it grow? So let's consider 2 scenarios, right? Scenario 1, n star is stable in the mean field sense. So let's consider this the case one. If n star is stable in the mean field model, what does that mean? What should alpha be? Alpha will be less than 0. Let's call this alpha k because it depends on k. What happens to alpha k? Is also less than 0, right? So this means that the kth, we call that, just called kth mode perturbation. Is it stable or unstable?
Stable.
Is stable. So does this meet your expectation of what you found with logistic model? If you win the logistic model, the carry capacity equilibrium was stable, right? And when you did numerical simulations, did you find that all perturbations were stable? I hope you did, and in fact, I showed you, right? It actually does. So what it shows that one specific mode is stable, though. Any odd now here is the thing. So all of you agree that the sinusoidal perturbation I made here will decay with time, right? It just collapses. Okay, eventually decays with time. And is this dependent on any value of k? Do you agree with this? Does this depend on k? Because the subtraction you are doing is an k square term anyway, all terms are negative. So this will be true for all k's, right? So the kth mode perturbation is stable for all k. And remember now that any perturbation is a summation of such perturbations, right? If not only a summation, but I'm very specific, it's a simple linear summation. I'm not doing any squaring or anything like that, right? So any perturbation, right, can be written as summation of such perturbations. Since every one of the perturbation dies, what does that mean? Any perturbation must also die if mean field equilibrium was stable. Let me know if you agree with this, with my conclusions. Does anyone disagree with my conclusion?
Sir, where did we take D into account?
D is, oh, I forgot D. Oh, thank you so much. There must have been a D here, no? D times this, right? So I forgot a D here. Okay. D. So alpha K depends on D. Is that clear now? So larger the D, larger the negative alpha K becomes, faster the decay. Does that make sense? So more diffusion makes the mean field equilibrium, you make the system reach mean field equilibrium even faster. That's a great point, by the way. I just totally missed D in the entire calculations. Any other questions? Okay, no questions. I will move forward. What about the unstable equilibrium? Oh, did I look at the stable equilibrium so far? Yeah, that's right. No, yeah. So what about the unstable equilibrium? If n star is unstable in the in-field model. So what does it mean? Alpha is greater than 0, right? So alpha k for an arbitrary k will be alpha minus d k square pi square by L. Is that right? Yeah. So now what happens? This is now positive. This is now negative, right? So will this entire thing remain positive? Positive minus negative can be positive and it can also be negative, right? So alpha k can be negative if d k square pi square by L is greater than alpha, or for k greater than alpha L square by pi square d. So which means that there are certain wavelengths of perturbation. Okay, so larger k means a lower wavelength or a higher wavelength. So larger k would mean a lower wavelength, right? So for certain wavelengths, it is actually possible that an unstable equilibrium would still be stable, right? So this means that some high, this is like, equal to high wave number. That basically means that low wavelengths, right? Perturbations can decay even though mean field equilibrium was unstable. Why does this happen? Primarily because of diffusion. So diffusion basically can make an unstable equilibrium stable, but only to some types of perturbation, only when they are low wavelength perturbation. However, let's think of the type of perturbations we might encounter. So the type of perturbation we encounter are unlikely to have, right, very specific type of wavelengths, right? So it may have a combination of high wavelengths, low wavelengths, and so on, and therefore the basic idea is that although some wavelengths can die off, what about small case? What about the case less than this threshold, right? Let's call this KC. All perturbations K less than KC will imply alpha K is positive, right? This means that they diverge from the equilibrium. If you do a random sort of perturbation, which will have all types of perturbations, all wavelength perturbations, effectively the system will be still unstable. So by and large, N star will be unstable to random perturbations. Containing K less than Kc. Okay. Is this clear to everyone?
Sir, should be k square greater than alpha L square by pi square t, right?
Yeah, thank you. So So Kc will be square root of alpha L square by pi square d. So any questions? So basically, broadly, we can conclude that in the populations we have studied so far, the diffusion does not change the equilibrium structure. This is one of those crazy things that happens, huh? I'll have to close and come back again. So put together, diffusion term does not alter the equilibrium structure and stability of the mean field model. And of course, the context is that reaction diffusion equations of this form. And although I have shown you all of this for one dimension, this should hold true even for two dimensions. Any questions before I move forward?
So how exactly does a periodic perturbation work when your mean field equilibrium is 0? So it'll be periodic, and I assume these are like perturbations in the population levels at that particular this thing. So if it's 0, you can't go less.
Yeah, that's a great point. You're absolutely right. So, so whatever I did will not work in such case, but you can do the following, right? You can always, let's go back up. It's a very good point you thought of. I can just elevate this up such that the minimum value is above 0. It is still periodic, right?
Right. So you can say k plus some other value,
Exactly.
p and p.
Yeah, exactly. Like, yeah, like this A0 term, you can, so the perturbation can be some A0 plus AK sine k pi x by L, where A0 is greater than AK. If you do this, then, you really cannot have a zero value, negative value. Huh? The minimum value of this will be 0 now. It can't be 1, 0. It actually will be A0 minus mod AK. It's basically shifting the entire sine wave up by A0 amount. Yeah, that's a good point. Very good point. But then everything that we have done still holds true, primarily because you can just repeat all the steps with a constant. So constant, this anyway, A0 will die anyway. It's a constant, right? A0 will die in this term, but the only place where A0 will not die will be the first term, alpha n term. It won't die there. It will again die in this term. Okay. So then you can do at that point of time, you can just do a variable change. And I think that will resolve the issue.
So when you say periodic in this case, it's periodic in space, not in time, right?
Absolutely, yes. Okay, exactly. It is in space. And the perturbation is introduced at time t is equal to 0, right? And then we see what happens after that. But the perturbation induced was a periodic perturbation. I showed you periodic as an illustration. But as I told you, any perturbation can be written as summation of all of this, right? So it holds, whatever I have argued holds true even if the perturbation was non-periodic. Is that clear to everyone, by the way? Although I showed you how a periodic perturbation decays, but the basic principle holds true for any perturbation. Is that clear to everyone, by the way?
Won't that be true only for a necessarily periodic system, or won't we have to like, isn't a Fourier series only for a periodic function? Again,
Yeah, so as I said, yeah, you're right. Technically, you're right. Fourier series is true only for periodic systems. So, so therefore, if your system was periodic, this is true. If it was not periodic, it is still possible to make all the claims with some small caveats. Yes. Of course, if the boundary is extraordinarily distorted and crazy, it is indeed possible that some results will change. But by and large, it holds true. So one way to think about this is, is my space so large? Okay, as I told you even when you are implementing periodic boundary conditions, right? So the focal area is really a small part of the entire landscape, right? So you can say it. So if there's a huge landscape and let me go to a small area, and in such a system, so you can sort of think of the entire system as periodic system of such smaller landscapes, and therefore we can apply this. That's one way. And of course, if you now begin to use the idea of Fourier transforms, that periodicity assumption is not even required. Okay, yeah. So I'll now move forward. We have shown basically that how to analyze stability for reaction diffusion system. Okay, so let me just do a bit. So I won't do anything new now. This is entirely a revision, by the way. So I just want to revise what we also learned when we have, coupled populations. For example, predator-prey, or it could be competition and so on, right? So what did we learn there? If there are two species, N1 and N2, right? The more general form of two species dynamics will be this, right? Okay, and again, we can define the idea of equilibrium here. Equilibrium N1, N2, they would be given by setting f of 1 is equal to 0, f of 2 equal to 0, and solve simultaneously. Okay, solve for root simultaneously. Those will give us equilibrium. What about stability? So to know stability, we need to compute something called Jacobian matrix, which is basically the idea is that we linearize these equations. Okay, we linearize, and when you linearize, you get all these derivatives, and the Jacobian will have these terms. The derivative of the first function with respect to N1 and N2, and likewise, second row will have the derivative of the second species growth function with respect to both the species. Okay, and then what do? We then calculate the eigenvalues. Eigenvalues of J. Okay, let's call them λ1 and λ2. If both λ1 and λ2 are less than 0, what do we have? We have a stable equilibrium. If any of them, of course, it's actually possible that λ1 and λ2 are complex numbers. So what we do is we look at the real value of λ1, and then we look at the real value of λ2, and then we have a stable equilibrium. However, if we have any of them, any of the real values is greater than 0, then we have an unstable equilibrium. So all of you remember this, right? Okay, another small trick to remember is that, let's call the Jacobian matrix terms as, A, let's call this A, let's call this B, let's call this T, C, let's call this D, okay? Then what we also know is that the trace of the matrix, that is A plus T, will be equal to lambda1 plus lambda2. On the other hand, determinant of the matrix of Jacobian matrix will be, which is AD minus BC, will be equal to product of the eigenvalues. Okay, this is just a revision, so please revise these concepts. We'll use them in the practice class. Okay, so that's it for me from today. For today, we will meet on Friday again. I can take any questions you may have now.